Okay, enantiomers have, unlike other types of isomers, identical physical properties. Okay, what that means is they have the same boiling point, the same density, the same melting point, the same polarity, the same solubility in common solvents. Therefore, it might be very difficult to tell them apart if you do succeed in separating them, except for one property. Solutions of enantiomerically pure chiral compounds rotate plane polarized light in opposite directions. In other words, enantiomers have opposite optical rotations. Okay, I've thrown a lot of jargon at you, so we need to deconstruct this a little bit. First of all, what is plane polarized light? Well, let's go back to physics and look at light. Light is an electromagnetic wave that propagates through space from the source to the observer. Okay, so physicists say that there's an electric field and a magnetic field that are perpendicular to each other as a light wave is propagating itself through space. What is important is that normal light, a light bulb, the sun, what have you, normal light can propagate through space in all directions. So this red electric wave does not have to be pointing up and down. It can be pointing in and out towards you or away from you. It can be propagating at any intermediate angle that you want. Okay, so light can propagate through space in all directions. When light is plane polarized, all of the electromagnetic waves are propagating in the same direction. What that means in reality is that you will take some kind of filter, put it between the light source and you, and block out any light waves that are propagating through space in any direction other than the one that is straight up and down. The light coming through this filter now has all of its light propagating in one plane, and therefore it is called plane polarized light. This type of filter is called a Polaroid filter, so that's where the polarized comes from. This is actually how Polaroid sunglasses work, to block most of the sunlight that's coming from the sun and hitting your eyes. If it only allows the light waves that are propagating straight up and down to get through, that blocks out most of the light waves and helps to serve as sunglasses. Okay, now in this diagram, if a second Polaroid filter is put in the same direction as the first, okay, so with its slits, so to speak, pointing straight up and down, the observer will see some light. However, if a second filter is put in a different direction, the observer will see no light in case B. The reason for that is the waves that are propagating straight up and down and can make it through the left-hand filter are now in the wrong orientation to be able to make it through the right-hand filter. Okay, so this principle is the basis for how we measure optical rotations. So we measure optical rotations using a device called a polarimeter. So you have your light source, you have one Polaroid filter that is fixed, that is called the polarizer, and then you have something called a polarimeter tube that contains the solution of your chiral compound. And as the arrows on this diagram indicate, the optically active substance in the solution causes the plane of the polarized light to rotate. So the light may be propagating in straight up and down at the polarizer end of it, but now as it gets closer to the observer, the plane of polarization of the emergent light is not the same as that of the entering polarized light. And then The other piece right next to the observer is called the analyzer. It can be rotated so that once the chiral solution has rotated the plane of light, you can rotate the analyzer the same number of degrees to match up with the rotation of the solution and therefore be able to see light coming through towards the observer. If you just kept the analyzer straight up and down, but the light's polarization has been rotated by the solution of chiral compound, you would see no light. So you have to rotate the analyzer a certain number of degrees in order to now be able to see the light come through. You can read that number of degrees off of the scale, and that is called the optical rotation. You report optical rotation as a piece of characterization data anytime you have a solution of a chiral molecule. Okay, so some notes about optical rotations. First of all, different chiral molecules have different optical rotations. Glucose is going to have one value, fructose is going to have another value, alanine is going to have yet another value. The optical rotation, the symbol for it is the Greek letter alpha in square brackets. And achiral molecules, molecules that are not chiral, do not have a stereocenter, have zero optical rotation. You could put them in a polarimeter and you will see the light coming through without having to rotate the analyzer dial at all. Secondly, if one enantiomer of a particular chiral molecule rotates the light clockwise or to the right, the other enantiomer will rotate the light counterclockwise to the left by the same number of degrees. Okay, that's an important point. Clockwise rotation is indicated with a plus sign, and it is referred to as being dextrorotatory for the root from the root to the right. Counterclockwise rotation is indicated with a minus sign, and it is called levorotatory. Okay, now the bad news. In the last lesson, we learned all about how to assign R and S to a structure. Unfortunately, there is no correlation, and I put that in big capital letters, between R and S and plus and minus. So just from drawing a structure and determining whether it's R or S, you cannot determine whether its rotation is going to be positive or negative. You can only determine if the rotation is going to be positive or negative by going into the lab, making up a solution of your compound, putting it into a polarimeter, and figuring out if the rotation is positive or negative. Okay, so some R molecules will have positive rotations, others will have negative rotations, some S molecules have positive rotations, and others have negative rotations. Okay, so an example of this, 2-bromobutane is an example of a chiral molecule. The R enantiomer, where the bromine is coming out towards you, has a rotation of negative 23.1 degrees, which means that it rotates the light counterclockwise, it's levorotatory. The S enantiomer has an optical rotation of positive 23.1 degrees, rotates the light to the right, it is dextrorotatory. Okay, so in addition to the fact that you have to measure the rotations experimentally, the converse of the bad news is that measuring an optical rotation will not provide any information about the three-dimensional structure. Okay, so if you have made a new chiral compound and somehow made it enantiomerically pure, and you know that it has a negative rotation, that does not tell you whether the enantiomer you made is the R enantiomer or the S enantiomer, and you cannot draw a correct structure with dashes and wedges for that compound. You have to use a different method, typically a method known as X-ray crystallography, in order to determine the absolute configuration of that molecule, figure out which way every atom is pointing in the crystal, and then you can correlate for that molecule only whether the R is plus or minus.